Okay, so today we're going to work to clean up, square up the front of this. There's a bit of a lot of cleaning for the edge we have to do. Kind of compress the spring, get this to where it sits in there nicely, along with any of the other ones that might be a little bit loose. Finish up completing this so it seals well with the door, and get to work on getting the electronics done, and hopefully at the end of this day we should be able to have this completely unit working correctly. I'm going to start by bringing this edge down a little bit. There's a little bit more to go. This is about our reference down here. That's how it closes. Little high spot right here. But otherwise that looks really good. So this wire's a little bit looser than what it should be. And since we haven't fired it yet, we're able to make adjustments to it. But once the wire's completely been fired, there's, just like we saw when we broke the other side wire, you have to heat it back up before you bend it. That's much better with the wires now. Time to get on the electronics. We've got a temporary kiln control in here. I looked at writing some software. The stuff that I've got doesn't line up with some of the example code. So we've set that up, and we're going to go ahead and initiate one of the kiln firing sequences. There we go. Got good warmth coming from both sides. What we have here is it's an Arduino Mega 2560. This is the only one I can program, and it will not run off standard input power. These are old. I've done crazy things with them. The other ones that I had were their inputs for the USB were burned. This is a SD card breakout board, and then this is a multiple button LCD keypad shield, and then I've had to use additional pins to pull out for the Max 6675 breakout which is what's providing the feedback in from the thermocouple. Where there's smoke, there's hella heat. So the spring's coming out right here. We can fix that after if we need to. We did go ahead and order a proper PID controller to mount. We have a fan to cool everything underneath, keep that organized nicely within its own setup. So we're gonna cut this faceplate out to have a square hole for the PID temp controller to mount in the face. We're not going to push it all the way in right now. We have to wire it all up. Nice. We heated it up to 600 degrees, kept it for an hour, burned off all of the binder on the fiberboard, and then we took it up to 1,000 degrees for an hour, and then we took it up to 1,500 degrees for about 15 minutes, and then slowly brought it back down. The only thing that we have left to really do is probably going to use a piece of wire to go ahead and completely secure this. It's a little loose, which is somewhat expected, and then this is a lot of the electronics we have to get back inside and wire it up, and that's what we're moving on to now. So we took an old PC fan, took 4 diodes, built a small full bridge rectifier, and we've got a 120 to 11.5 volt transformer that we're going to put as part of a cooling mechanism for the relay. So with the existing heat sink mount for the relay, it's a little too tall. It'll put the relay too close to the bottom of the hot surfaces. So what we're going to do is we're going to cut this off, drill in from the bottom to secure this underneath the fan. As we had discussed, we'll keep the mount the transformer right behind here so the fan blows across the transformer as well, and then go ahead and connect everything else up electronically. So now we need to affix the relay to the heat sink. Alright, that's connected. Then our cooling system. We're just going to use this existing mounting screw. The fan is blowing the air across the relay, the heat sink, the rectifier for the fan, and the transformer. So it should keep all of this nice and relatively cool. In the on position, not that way, not that way. Okay, so it's just straight through.
Here. Okay.
And we'll lock the switch into place. Awesome. So then we have the door switch, which is also going to be a disable for the relay. It's not going to turn the PID off, but it is going to control the relay.
Close it. Cool. Open it.
These are all of our previous connections while we were doing the testing. So we have input power connected to the power switch. Power switch comes on, power comes out on the black and the white wire to these two red wire nuts. Part of the power coming out of the red wire nuts goes to the transformer, turns on the fan. It also comes over to the PID controller on the bottom side for its AC input to bring this online. And then part of it branches over to one half of the relay, and the other half goes off to the neutral side of the coils. Then we have on the relay output from the PID, it goes over to our enable switch, which indicates a light when it's on and everything is up and running in conjunction with the activated relay light. And that is in series with the door switch. So this switch has to be in the up position, the door switch has to be closed in order to activate the relay. And let's take a look at how that works right now. So we're on, and right now the input light on the relay is not active. If I engage the relay, this is showing that it's blue for on. This is not active. If I close the door, now we have red, and you can hear the hum of the coils themselves right now running. Current load is about 7 amps per coil side. And then when we open the door, it should shut off the coils and make them safe. Yep. The relay light has gone out. This light remains lit. I could also have disabled it from here. So, other than finalizing these two plates, which right now they're a little bit too long and a little bit too wide to just go on in as a good base, I think this is complete. Let's go ahead and get it on. So, with the switch down, we can turn it on. Get our set temperature. Right now it's let's bring it down to 550 degrees Fahrenheit. Okay. Close the door. There it goes. Alright, so we're going to verify where we had set this at before. We did have it set at 550. It overshot by apparently 15 degrees. It's wanting to hold there. So the PID, this one, it's not exactly the best. It was a cheap one. This was $30. The fan we pulled out of an old computer years ago. The transformer came out of something years ago, free. The diodes, I probably bought those in the 90s. I went through 4 other ones. One of them was bad, so I just built another bridge rectifier. I have no idea what that replacement cost would be today. The replacement coil was $10, about $10. The bricks were $27 for 4 bricks. I used one of the bricks. The fiber board, I can't remember what that was, probably 40. I've got a full sheet of the stuff left. And the unit itself, I bought 3 different furnaces in roughly the same condition as this one. Some had bad electronics or temperature control, and some of them had bad coils. I bought 3 of them for 60 bucks. So the other 2 should be about the same to get these back up. We'll probably use a different controller on there. I did want to use the Arduino, which has a lot finer control on it. But the unit runs great now, other than the heat ramp overshoot by just a little bit. If we had a part in there, the overshoot is not going to take the part over the temperature we want it set at as if we bring it up. And we're never going to bring a part up slowly with this where it's programmed to be above the set point. We'll bring it up close to that set point and then raise it the rest of the way up to the set point. And as you can see right now, the alarm has gone off. That's set low at 400 degrees. I'll probably reprogram that to have an alarm start sounding at 2000 degrees Fahrenheit. So if we ever get too hot, it starts to just scream. I'll put a speaker in there. And then now, as you can see, it's coming down to the set of 550 degrees Fahrenheit. And it's just going to pulse and keep that temperature where it needs to be. Just take a quick look. So the coils have turned off. We used a pin to support this one. Put a pin in here and another pin up in the front. And now it's sturdy in place. This one doesn't wiggle at all. The area inside is nice and toasty. And the temperature's rapidly falling back down. We'll close it and give it an opportunity to start coming back up. So we're going to use this to melt aluminum for casting. We'll also use it for the heat treatment of various tool steels for making tools or components and pieces that we will be making in the future. One of the first things we're probably going to end up heat treating are going to be taps to tap the new lead screw nuts for the other machines that we'll be bringing online. And thanks for watching. This is a good completed unit.